the sign-up sheet. Okay, so I'm going to get just your initials on this to make sure you're here for the first day attendance.
There's a spot that personal face you mentioned and I can sign for that spot, so it might be my name.
Yeah, that's fine. You'll just put your name at the bottom or on the back, okay? Name and U number, initials and U number. But before we do that, I want you guys to sort into the groups I have up on the screen, okay? So you see 1, 2, 3, 4, 5, 6, right? And hopefully, yeah, I think you can kind of see everything. Let me pull this up. It'll be a little easier. Yeah. And I want group 1 to be at the front, 2, 3, 4. We only got 6 rows. Let's see how it sorts out, okay? But everybody start grouping up. So 1, 2, 3, 4, 5, and maybe 5 and 6. Okay. See your name up here? Yeah, so whatever group you're in, get into the corresponding row, and I think 5 and 6 will hopefully fit in the back. No, we'll figure it out. And it won't be, you won't, just sit here most days, I guess. It won't be every day that we'll have group activities, but it'll just be more convenient instead of having to move around so much. This is group 6. 6 and 5, right? Yeah.
I'm 5.
Okay, so 5, I'm sorry, 5 on this end and 6 on this end, okay? And if you need to, like a couple people from 6 can sit here, and then you can turn around when it's time, okay? What group are you in, buddy?
Group 1.
Group 1, yeah, just come on down here somewhere. Oh, and you guys don't have a group yet, right? Why don't you come to group 1, and you're new as well?
I signed up last week, but it's not there for some reason.
Are you sure you're in the right section? What's your name?
Erica?
Erica what?
Lopez.
Yeah, I don't have you in the other section. Yep. Okay, just put your name and your U number on this sheet of paper. Okay. Let's see. You have the U in 1. What do we got? We got 4, 5, 4. Yeah, you can go in group 2 for today. Okay. Check your name and see which group you're in. What group are you in? 2. Okay. Why don't you go to group 4? Okay. No, I'm sorry. You're gonna stay in 2, and then she's a new person. I'll get it, and you know, I may change the groups based on the, you know, people coming and going with the dropping and adding from this week. But this should be sufficient for today. Okay, so start. Find your name, put your initials and your U number next to your name, and let's pass that around. And then the last person to get it. Bring it back up to me, okay? Okay, so while we're doing that, I need you guys to sort some beads, okay? So we're gonna need 40, and I'm trying to get them separated, okay? So 48 beads, red beads, 48 green beads, okay? Go for it.
Thank you.
Don't waste my time.
Here you go.
It's a surprise. We'll get 48
I've never been in a class this small.
I'm also confused because all my lessons have been in this building, like up and stuff. I'm just like, huh. I was like nervous. I was like, are we literally just sitting like?
Are you guys counting together? Yeah. You only need 48, okay? So can you count to 48? Will you check your, hey, wait, excuse me. Will you check your name on the list here? What group are you in?
Either because I switched because I first was enrolled in Ortho 2.
No, I'm just on this list here.
So I just swapped it last time. Oh really?
Yeah, so go in the third row right there.
Oh yeah. So I swapped it last minute. I couldn't look it up. And then there was one spot that opened yesterday, but it overlaps my genetics like by 5 minutes. And I was like, I can fade the last 5 minutes. Of my genetics. I know they won't let you do it.
Like I would so like.
Just like skip the last 5. They were in the same building. It was like I would go upstairs.
It's not even like you're walking across the
Yeah,
campus.
because my genetics was in like the lecture hall that night. And then it was like one of these things. I was like, I should walk upstairs and like miss the last 5 minutes and then
You guys got 48? 48 residents?
Are you in genetics too, right? I'll tell you about it. It's basically like, it's a research experience, but it knocks out credits for both cell bio and genetics lab. I
Is this
mean, it
48?
is so.
How do you get in it?
You can just put all
To
the
email your advisor, and it's like a separate whole separate thing. They don't like talk about it because it's like.
Well, I have an advising meeting on my board. I need to do like more ad drop.
I was gonna say,
No,
I
no,
think
no,
it would
just
be
the
easier.
extra,
Yeah, let me do that right now.
That's 48.
I can like show you the syllabus.
Then you don't have to do.
You only need
genetics
48
lab
of
and
one
that.
color, guys, okay?
It's so cool.
Wait, I'm doing that right now.
Then we need 48.
I never emailed specific advisor. I just do like the county guys.
Yeah.
Yeah, sure, but I need you to put 48 on one side. Get 48, put them on one side, and put the remainder in there. Okay, and everyone's passing around the sign-up sheet, right? Where is it now? Okay. Initials and U number on the sign-up sheet, please. Okay, and now I'm gonna pass out 2 handouts, okay? And one of them is gonna be used for the bead activity, and then the other one is gonna be for you guys recording and working on the problems that I have assigned today. What's your number up here, buddy?
2.
2? All right, you're in this row. Who did I assign to 2 at the last second? It was you? Yeah, why don't you, so who's in 5? 4, okay. Yeah, go back there with group 6, okay? But actually sit in this table here, and then you can turn around, okay? Is that cool? All right. Okay, pass this around and take one. Give one to her as well.
Thank you.
Yeah. And don't start working on the problems yet, okay? It'll be a minute. And then take one and pass that one around. Okay, so my name's Professor Dodrell. I'm going to be your instructor of record for cell biology. We are going to start, so typically I'll have about 30 minutes of lecture. As we get on in the class, the lectures will get a bit longer because the material gets a little bit deeper. And then we're usually going to spend the rest of the time solving problems that are related to the material in the lecture, okay? And so it's going to be essential that you guys come to class. I think I give 3. You can look in the syllabus. You can miss 3 of these in-class exercises, okay? But they're live, and there's no way to make them up, right? So there's going to be no makeup for in-class exercises. But if you miss 3, then it won't count against you. If you miss more than 3, it's going to start counting against you. Did anyone look at the syllabus? Does anyone have any questions about the syllabus before we start? Make sure you look at that by Wednesday, okay? That's sort of our contract for working together. Make sure you understand all of the assessments. We're going to have 3 flavors of assessments. The in-class activities are going to account for about 30% of your grade. We're going to have 2 exams, one midterm exam and one final exam. Those together will be 50% of your grade, and then the last 20% is going to come from online quizzes. And so I'm going to talk about in class, when I give lectures, I'm going to talk about stuff that I'm interested in. Why did that happen? And then I'm going to leave it to you guys for some of the more basic material to get that out of the book, and that's what the quizzes are gonna test your knowledge of, okay? All right, so have we finished the signing, and does everyone have the 2 handouts? Everyone have their beads sorted too? I can take the rest, let me get the rest going here. I do with a jar. Does anyone see my jar of beads? There we go, thank you. So each group is only going to need 48 beads. And sincerely, I used to have a better holder to separate them. So where's your 48? That one. And then this is your extras. Okay. Yeah. Okay, who's got extra beads? Pass this around and put your extra beads back in there, okay? And so each group should have 48 beads, and I'll show you what we're gonna do with that in just a few minutes. But first, before I do that, I want to see what you think and know about concentration, okay? And so what is concentration? What are the typical units we use to talk about concentration when we're talking about liquid solutions? All right, what's your name? Let's see. Last name?
Okay with the pencil. Okay with the pencil.
And so where are you on this list? Which group? 4. Okay, you need to be in the next row there. so we're typically gonna be working in water, right? That's what your cells have inside of them. What else do your cells have inside of them? Hmm?
Solutes, or like concentrations of ions and chemicals and molecules.
What kinds of molecules? What are the big ones? What are the big 3 or 4?
Carbon, hydrogen, oxygen.
Those are atoms. Big molecules.
Carbohydrates, proteins, lipids, and nucleic acids.
There we go. Thank you very much. Right. So that's the big 4. We're going to want to understand how the cell concentrates things, right? Because that's how a lot of biology happens. The cell is a reservoir, and there's going to be very tight control on things that get inside and out of the cell, and we'll talk about that in more detail. But I just want to, assess your basic understanding of what concentration is, right? So it's the amount of stuff, and we usually call that the solute, that's going to be dissolved in some solvent, right? And so you don't always have to have a solvent. A gas has a concentration as well, but we're not going to be worried too much about the concentration of gases, right? There are some diffusible gases, obviously oxygen going in, carbon dioxide coming out, but we're mostly going to be focused on concentration in a water-based solvent. And so why do things dissolve? So if I add a bunch of protein to water, add a bunch of salt to water, why does it dissolve? It doesn't stay in a crystalline form, right? What's happening? Just give someone else a chance.
Ionic bonds are breaking into
Okay, so sodium and chloride are held together by ionic bonding. Why are they breaking? What is it about the water that causes them to break? So water has a permanent dipole, right? And so it's gonna overcome because there's so much water, okay? And so a really concentrated salt solution, that would curl your toes if you took a sip of it, would be like 1 molar sodium chloride, right? What's the concentration of water? How would you go about figuring out the concentration of water? What would you start with? What property of water do we know about intrinsically? How could you figure out how many molecules are in a liter of water, right? That's the sort of molarity definition that we're looking for. What would you start with? Check your name up here. So where are you at? Yeah, which group are you in? Okay, so that's gonna be on the left-hand side of the back row there. Actually, I don't think there's any more room. Why don't you just join section 2 up here for today, okay? What could we use? We just know that there's water. We know what its molecular weight is. What else do we typically know about water? What does density mean? What's density? What are the units of density? Mass over volume, right? And so density of water, it changes, right, when you have ice, but density of water is around 1 gram per milliliter. And we know the molecular weight of water, right, 18 grams per mole. So you can get there, you can get to molarity from just knowing those two things, and you look at water and it's about 55 molar, okay? The molarity is quite high, and so even though that ionic bond between the sodium and the chloride is quite strong, the water is going to have enough of these polar interactions with the positive and negative charges, because, you know, one side of the water has a partial negative charge, the other side has a partial positive charge. Which side has the partial negative charge? Which atom on the water carries a partial negative charge? Oxygen, and that means the hydrogens are going to have the partial positive charge, right? Okay, so here's various sorts of units that we use to describe concentration. They're not all up here, but as I said, the one that we're going to be working with is molarity, right? And so does everyone remember how to do basic concentration calculations using molarity? Okay, you're shaking your head. What is your question?
Oh,
It's been a while. Okay, but you think you can figure it out? Okay, good, because that's what you got to do right now. Okay? All right, so I want you to figure out the molar concentration of hemoglobin in a red blood cell. All right? That's the first question on the handout I gave you. And so the handout with the questions on it, you're going to put your name, you're going to put your U number. Who doesn't have the handouts? Yeah. Let's get that sorted. Just one other person? Everybody else has them? Yeah? Okay, so you've got about 300 million hemoglobin molecules in a red blood cell. And remember, hemoglobin is a tetramer. It's formed from 2 alpha and 2 beta forms. But that's what the molecular weight is for the tetramer, right? You don't necessarily need that to solve this. Average blood cell is about 1 × 10⁻13 liters. And of course, Avogadro's number is 6.022 × 10⁻23, right? And so I'm going to have a lecture on how you generally set up these kinds of problems, but what are we going to start with? What are we going to end with? What value up here is the value that we're going to start with to calculate concentration? So yes, figuring out the moles is a good thing, and I've given you the number of molecules, I've given you the volume, and I've given you the conversion between molecules and moles, okay? And so at the end, let's think about the end, right? So at the end, we want to have moles per liter, right? But what is the first thing that I'm giving you? What do you have to use? What number do you have to use to figure out what your moles are here? The number of molecules, right? So that's the first thing we're going to have. 300 million molecules. And what's the number we're going to want on the bottom ultimately? Huh? 1? What units do we want on the bottom? Okay, so what number do we want on the bottom? 1 × 10⁻13 liters, right? Okay, what's next? Yeah, so divide by Avogadro's number, right? Thank you. And voila. Okay. Tell me what you get. And so you can use your phone, you can use a calculator. You gotta, you know, one thing that I'm trying to get you to do here is to sort of work with exponents, okay? What's the easiest thing to do here, right? What's the first thing you can do? What can you do with this and this? Yeah? Add them, right? And so what do you get when you add them? 10, right? So, yeah, so this basically goes away. And this ends up being to the 10th power, 10 to the 10th power. Those are all my extras. Thanks. All right, anybody need more time? Yeah? What'd you get? Go ahead.
Well, I got 4.98 times 43rd.
10 to the 43rd. Okay, remember, this is a negative, right? This is a negative and this is a positive. Okay? And so what do you do with exponents when you multiply them? Yeah.
You multiply them, you add them.
Add them, and what do you get if you add 23 to minus 13?
10.
Yeah,
Yeah.
yeah. So why don't you try that? Okay, I think your base is correct, okay? But what should the number be? -3, there we go, good, all right? And so, typically in biology, so you know, things are in molarity, right? But in biology, we'll typically, because molarity is a lot, okay? We'll typically represent things in millimolar, which is, you know, molarity times 1,000, okay? So approximately 5 millimolar is the concentration, average concentration, okay? Because remember, every blood cell is gonna be a little different size and it's gonna have some more or less hemoglobin molecules in it. Okay, questions about this calculation? Everybody feel good about it? Everyone's like, yeah, can't wait to do some more molarity calculations, okay? All right, now we're gonna talk about equilibrium, okay? So equilibrium is kind of a difficult concept to grasp, And that's why we're gonna do our little bead exercise, okay? And so equilibrium is going to give you a certain ratio of reactants and products. And what ultimately is that ratio going to depend on? What is the constant that we love to talk about when we talk about equilibrium? What is that constant called? We talk about equilibrium, there's a constant that we talk about when we talk about equilibrium. What is that constant called?
Okay.
Come on, guys, let's go. Yes. The equilibrium constant, right? And so how do we define KEQ for the simple reaction that's written up on the board? You just, you know, basically all you have, you just got one thing happening here, right? You don't have multiple molecules. I'll put it over here. You've just got some simple conversion of A going to B, right? And so how do we define the equilibrium constant? What is KEQ equal to? For this reaction, what is KEQ going to be equal to? There we go, products over reactants, right? So the concentration of B over the concentration of A. I've got to go, there is no, be right back, okay?
Section 2 does not make sense.
As long as whatever decision is up on test, like I don't care.
That's
So count out 48 beads, okay? Who all has 2? You guys got 2 for 48, right? Okay, so hand one down to this end, to these 3 folks. You guys got 2 with 48? Yeah. Hand one down to the 3 folks at the end. You guys have 2 with 48? Okay. Hand one down to the group at the end. You guys have 1 with 48. Make one more, because you want to split you guys into 3 person groups, okay? So take 48 of one color out of there and put it in here, okay? And let me see those colors. Okay, and you guys have 1. So who, and you're 6 for today, right? Just 4? Who's out there? Are you 6 or 5? 5, okay, great. Yeah, so 4, you guys can do yours, that's fine. Okay, so
I think it's 48 the same color.
within your bigger groups, you're gonna have, like groups of 3 or 4, okay? And so this is the way this activity is gonna work. So you're gonna figure out, starting with all of your beads in the A state, right? You're gonna figure out how long it takes to reach equilibrium. And remember, the important thing about equilibrium is you're not gonna end up with an equal number of products and reactants. What is the thing that's equal when you reach equilibrium? Huh?
The rate is constant.
The rates are constant, that's right, and that's because of the difference in the concentration on both sides. But the thing that's equal is the number of molecules going back and forth between the two states, okay? And so hopefully this bead exercise is gonna help you guys demonstrate that. So you're gonna make a chart. And so someone can be the person passing beads back and forth. One of you can be the chart taker. Someone else can be the bead counter, right? And you guys can figure that out. You can decide what that's gonna be. And if you look on the other handout that I gave you, right? The first 8 steps of the activity is what I want you to do. You don't have to do step 9, but you're gonna have, you're gonna make a chart. And your chart is gonna have 5 sections. Your first section is gonna be what round it is, okay? So this is gonna be your round number. Right, and so it could be 1, 2, 3, 4, until you reach equilibrium. The second one is gonna be what you start with in A. The second one is gonna be what you have in B, and you're gonna do it each step, okay? So every step, you're gonna have a certain amount, and then you're gonna have how many you move from A to B, and how many you move from B to A, okay? And obviously, for the first one, you don't have anything in B, so everything's gonna be in A. You're gonna start with A. You're gonna have none in B. And then the rule that you're going to use when you move things back and forth is when you're going from A to B, you're going to move 1/2 of the beads. And so you're gonna make a step, right? And so after this first step, then it'll be 24 and 24. And then the next step, you're still gonna move 1/2 from A to B, and you're gonna move 1/4 of your beads from B to A. And you keep repeating this until you reach equilibrium, which means you're transferring the same number of beads between the 2 piles, okay? So equilibrium is not gonna be the 2 piles being equal. It's going to be when you reach the point that you're transferring the same number of beads between the 2 piles, okay? So you guys talk amongst yourselves and figure out who's gonna take the notes, who's gonna move the beads around, who's gonna count the beads, and you know, you can set it up however you want, but I do want you to have a little discussion about it. And before you do that, or while you're doing that, make sure you introduce yourselves to each other, okay? And so I'm gonna give you about 5 minutes for introductions, and then maybe 15 minutes to finish the exercise. At the end, you're gonna calculate the equilibrium constant, okay? And you're gonna put that on the problem set. That's the second question on the problem set. All right, have fun. You can go with these guys, okay? Yeah. So you got 48 here? Okay. the instructions, okay?
Yeah, I'm Peter.
What's your name?
Daniel.
I'm Kaylin.
Peter.
So all you four guys.
I'm Peter.
Together,
Peter.
okay?
Dylan, Peter.
So it's gonna be like the beads out. Okay?
I guess you're taking the
Actually, what
chart.
Huh?
Taking the chart.
Put them in there.
Yeah.
I don't have 24.
What are the three rules? Charting, counting, and what?
Right here. The A beginning, B beginning, A to B, B to
But like the what will we do? Like you're gonna chart it?
A. I guess. Like, I don't get what we're supposed to do with that. They're all the same color.
And you're gonna take half of them, you're gonna move it over here. And that's step one.
You let us have it.
And then step two.
So you have charting, counting, and
Right? And then
It's mostly just
that
math.
step
yeah.
until the number that you're moving.
All right, let me count this to make sure that we have the actual.
And make sure you write it down, okay? Make sure you make your chart along the way so you know.
So, so A to B transfers half, and B to A transfers 1/4.
Yep, A to
Okay.
B transfers 1/2, B to A transfers 1/4. Okay?
Well, 30 isn't divided by 4. That sucks.
Yes.
7.5.
Yeah, so your first step, you're only moving from A to B. Okay? Because there's none in B. But then your second step, you move half of A to B, another half.
And then half of another
No, a quarter of B goes to A.
Yeah, 1/4 of B goes to A. See,
A quarter of B goes to A.
yeah, we don't get whole numbers, I
Count your
think.
B's again and make sure you get a B.
Does this look right?
I don't know because you wrote fractions up there.
Yeah, the half of what the original population, I think.
And then the rest of it. Minus step one, not minus one.
I don't know. It feels weird. Huh?
It always has to have.
Number 3, if there's now 12 and then 12.
I'm lost.
Yeah, but we can't. Oh, I thought you were saying there's 9 of each. Like, yeah. 21, and then that would be 7. And then
3.5.
No, you gotta have 1/4 of the initial.
So the 24.
and then
So remember, guys, at this point, right, things are moving back and forth, okay? And so half of 24 is 12. A quarter of 24 is what?
6.
Okay?
I feel like I'm not doing this right.
And if it's an odd number, I think you're supposed to round up by 1.
Oh, well, you
Or
get that.
just keep it odd, it's fine.
Oh. Well, if you get decimals.
A by
Yeah, I'm just writing it down.
I know, but I don't think that's the number. 21 divided by 10.5.
Yeah.
Are y'all getting decimals?
Yeah.
Okay.
27 divided by
Yeah.
8.
But it's not 27.
Yeah. Oh, it's 27.
Yeah, now,
So that would be 37.
yes, yes. Wait, 39 should be 37.
What's 9?
That's what I was saying. I don't know. Yeah.
But,
it's 12 and 24, then you're also adding 6. And then we're getting rid of the 6, but you're adding 10.
I have to do this again.
You did
So this
24 divided by 3.
Yeah, that's okay, you can repeat it, right?
Yeah.
Yeah, do it again if you're not satisfied.
Divided by 2
I see the
is
beats?
12.
That's right.
You have the quarter of 24, which
Is that an extra beat or is it the beat?
That's the extra beat.
Oh, it's I think one told me for. Oh.
I don't know, I'm lost.
and then 30 on the other round. And then we did the same thing here. So 18 divided by 2 is 9.
Do we each need to do the table, or is it just one?
I don't know.
7.5. So 7.5.
Okay, I'm sorry, here is the detail if you end up with a fraction, right? It's the last sentence under the try this, okay?
I think one of them
Um,
one of us will keep track in the chart
so
while one of us counts.
If you
And
perform
then
a
we'll all just
calculation
copy
that
the same
results
chart
in
at
a
the end and
fraction
think is how
of
that's
a
supposed to
point,
Yeah.
round the answer
I'm just gonna
down,
do
okay?
I mean, ideally, there is a decimal which is equally.
But did you hear what I just said?
Yeah.
Yeah, either way.
I'm just saying ideally.
No, not ideally, quantitatively, realistically, if you do the math.
You said take like a decimal to round it down.
Yeah. Yeah.
So let's do 16 and 30.
Yeah, so if you get a fraction of a bead in your calculation, round it down, okay?
Well, it was 31.5, right?
So this was 7.25.
Is it 18? So 18 divided by 2 is 9. Plus
Yeah, it's somewhere it evens around 5, something like that. But if we just
Well, that doesn't add up.
do alternate,
Yeah, 48.
kind of 9.
No, you're good. Okay, so we 31 and 7.
So that's what it's supposed to be.
For 16, okay, what's the number?
6 rounds up.
So 18, 30. So round down, so that would be 9 and 7. And then we go from there. That would be 16.
This one's right now. It was 16, or it was 17.5.
Which round was it?
It's 18 divided by 2, so it's 9.
The third round. Every
Yeah,
round.
that's
So I
it.
just,
30 divided by
I just
2.
pretend we round it down.
And then 7.5.
And then on the fourth round.
Because this is 30.
I'm confused.
Oh, okay, so yeah, we got it by round 4.
You might want to do one extra round to make sure.
So yeah, they both transfer 8. So 5 would be, that would be 8 plus 8, 16. So yeah, 32. So the first one is, so which round are you on?
I'm on round
3?
I guess because I moved half of A over B and then I moved 1/4 of B over to A.
Yeah.
So now we're at starting for round 3.
Okay, so if you start round 3, you should have 18, 30.
And then I'm like,
18 for A.
I know, it is
Yeah,
weird.
18 for 8.
By the rounding, I'm confused. I know.
Yeah, you just round down. You
Yeah.
get it
Well,
by
I know,
round
we're
4.
just saying like it's just less than the 48, so it's like off.
Yeah, sure. Because that's if you do that.
Yeah.
Yeah. If you round down, you just get 8. That's right.
16, 31.
32. Yeah, because you
We
gave
had
what?
31.5 though.
Huh? Yeah, but that rounds up because you're rounding the
I know,
7.5.
but he told us to round down.
Yeah, you're rounding the 7.5 to 7.
Yeah, but you should also, she's saying for the 32. She's saying she got
No,
31.
because the 31.5 comes from the 7.5. If you round the 7.5 down to 7, it's, yeah, if you round if you do 30 plus 7 minus, 30 minus 7 plus 9, that gives you 32. Instead of, because yeah, you're ignoring everything after the 7.5 because the 7.5 is different.
Where are you getting these decimals?
Oh, those were just like when he didn't say, I didn't say the round down, yeah.
24, 12.
Sorry, because I used to have that.
We're at 16.
24, 12.
16 and 32.
Yeah, 16 32, yeah.
So not even 48.
Yeah, yeah.
So like, after 5 rounds,
It's 4. This is it.
Yeah, if you do the decimals, eventually you can just apply the integral to integrate to 1632. Lim where x reaches infinity. It's fun.
Okay, here's my bid.
It's annoying how it makes a decimal. Yeah, I mean both.
Okay, who needs some help? Does anyone need help?
So 16.
Is everyone at equilibrium? Who's not at equilibrium? How many steps did it take you to get to equilibrium?
4 steps. If you round down.
Did you do one more to make sure?
Yeah.
Did an extra?
It doesn't have
Yeah.
to be the same number.
All right, so your chart should end up looking.
It's eventually when lim reaches infinity.
You guys get it?
Yep.
Can I get the extra bead?
Where is it?
Fun. Alright, so equilibrium constant. So K equilibrium is equal to final of pile and pile of B. So it's just 32 over 16. So it's equal to 2, yeah.
So now we're at 10 and 30. Because we transferred half of the 20.
Yeah, it's a self-contained infinity. That's fun.
These bits. Okay. So 4 rounds, right? And then do one extra round just to make sure nothing changes. Okay, so we don't have to worry about volume in this example, right? But at the end, we have 16 beads in group A, and we have 32 beads in group B. So what's our equilibrium constant? 2, right? Okay, make sure you put the work on the sheet, right? KQ equals A equals B over A, and then show me the answer, okay? All right, any questions? Okay, pass the jar around. Put the beads in the jar and then pass the plates around too so I can, because I gotta do this again this afternoon, okay? Collect all my plates together, that'd be cool.
Big note.
Okay, so we know there's typically going to be directionality in these reactions, right? And so I'm gonna talk a little bit about coupled reactions because this is happening all the time in biology. And then I'm gonna talk about how we figure out whether or not a reaction is gonna be spontaneous. And so coupled reactions, you can drive a coupled reaction if simply one of the reactions is spontaneous, okay? And so what does that mean? That means we have X converting to Y. And actually in this scheme, remember the larger arrow corresponds to which way the equilibrium is favored, right? And so this would normally want to stay in state X, but we need it in state Y so we can make Z, okay? And you can see that going from Y to Z is much more favored than going from Z back to Y. So even if we make just a small number of Ys, they're going to very quickly be converted to Z. Okay, and so what does that mean for X and Y? What's gonna happen to X and Y if Y is quickly converted to Z? Yes?
You're always gonna have more X's than Y's.
You're always gonna have more X's than Y's, but after you rapidly convert a lot of your Y to Z, what's gonna happen?
Your concentration of X is gonna go up.
Yeah, your concentration of Y is gonna increase because you've got to maintain the equilibrium, okay? Does anyone remember what this is called, where you're siphoning something off of the product to drive the reaction? What is that called? French dude? Le Chatelier's principle, right? Okay? And so, if you're doing something with Y that's taking it out of the pool, then your equilibrium is always gonna readjust, okay? And so you're still gonna maintain this balance. The relative ratio is not gonna change because you're not changing the equilibrium constant, but the total numbers are gonna decrease in both of these categories as you rapidly convert Y to Z. When you do this, even if you have, so in this case, they're showing an unfavorable reaction and then a very favorable reaction, okay? And if we want to think about the energetics of this coupled reaction, what are we gonna do with the energies? What mathematical operation are we gonna perform on these energies? So we've got an energy going from here to here, it's non-spontaneous, okay? So what does that mean? Is delta G gonna be positive or negative? What's delta G? Named after another dude. Unfortunately, at this point in time, it was almost all dudes, okay?
Gibbs.
Gibbs free energy, right? The Gibbs free energy, okay? And so the first reaction, and this, they're talking about a real reaction here, right? So they're trying to couple this glucose 1 phosphate and ADP production to putting glucose and fructose together, okay? And so the first reaction is unfavorable because you're breaking bonds, and so it's got a positive delta G. The second reaction is favorable, it's got a negative delta G. And so your overall free energy for the coupling of these two reactions is gonna be negative, which means it's gonna proceed in a spontaneous manner, right? And so as you lose Y is gonna be replenished from the pool of X because of the equilibrium that's established. All right, so we talked about just conversions, okay? And this is a very simple way to think about it. But in biology, a lot of what we're gonna be talking about are gonna be interactions between molecules, right? So proteins are gonna bind to ligands, they're gonna bind to substrates, they're gonna bind to each other, they're gonna bind to DNA, okay? And we're ultimately gonna talk about protein assemblies that can have 20 or 30 different protein molecules associated with them, right? Doing very complicated things in your cells. And so we need to think about a formalism to treat something like that, to figure out the energetics of something like that. And it may not be obvious, but we can't do it all together, right? We can't measure all of those energies simultaneously. And so how do you think we're gonna break it down? What are we gonna do? What's gonna be our easiest thing to do if we have 30 different things that are interacting with each other. What are we gonna try and figure out first? What do you think? Are we gonna try and do 5 at a time? 10 at a time? How many at a time are we gonna do? What's the minimum number that we have to do? 2, right? 2 at a time, okay? And so association reactions, then we're gonna take 2 things. We're gonna take a protein, we're gonna take a ligand, we're gonna put them together and make a complex, okay? And so we can directly measure the energetics of these types of interactions. If I have time, I'll talk about some of the techniques that we use. And so we're gonna change the nomenclature for the equilibrium constant just a little bit, okay? And so when we're going in this direction, when 2 things are coming together, we're gonna say that's association, right? And I'm gonna use this little subscript A. And so, but it's still the same ratio, right? It's the concentration of the products over the concentration of the reactants. So remember, you know, reactions are typically reversible. They're not always reversible, and there's a lot of things that are driving irreversibility in biology, but when I'm just trying to get you guys to understand what's going on here, we're gonna think about it as reversible, okay? So what does that mean that we can do? If it's reversible, we can just flip this equation by 180 degrees, okay? So we flip it around this way, and now we have AB going to A plus B. This is a dissociation reaction, and so I'm gonna call that formalism K sub D for dissociation. So this is the dissociation constant, okay? Now, what are the units of the association constant going to be? I've got concentration over concentration squared. So what are the units gonna be once I do the math? If I have X over X squared, what do I end up with? 1 over X, right? Okay, so 1 over concentration is kind of a clunky unit to deal with, right? We like to think about things in concentration. And that's what happens when you turn the reaction around, okay? You put the reactants on the top and the product on the bottom. We switch the reaction, so now it's opposite, okay? So it's the products on the top of the dissociation reaction and the reactant on the bottom. This gives us a really nice, easy, sort of simplified way to think about this problem, okay? Because we want to work in concentration. We want to work in concentration because we want to know the concentration of all the molecules in the cell. We want to know the concentration of all the molecules in your blood, circulating concentrations, right? That gets us to thinking about drug development, okay? Because you're not gonna take 1 over the concentration of some drug, right? You're gonna take a couple 100 milligrams of ibuprofen, and that's gonna be diluted in however many pints of blood that you have. And so by using, by kind of turning the reaction around a little bit from the normal way that maybe you've thought about it, we get to a point where we can think about, okay, how much stuff do you need to take for it to have a particular effect, okay? And so dissociation constant is really easy to model, okay? And so for the association constant, the bigger the number, the more product you're forming, okay? It's gonna go in the other direction for dissociation, right? The smaller the number, the more product that you're forming, right? And so the smaller the number, that's going to mean tighter binding, okay? And so this is log of your protein concentration. And so KD, when that number is smaller, that means it's gonna be tighter binding, okay? And here's what your delta G's look like for both of these cases. So with the association constant, it's typically going to be a number that's greater than 1. Okay, but that still means a spontaneous reaction. Okay, and so you're going to have a negative sign in front of the relationship between your Ka and delta G. So here's your association constant. What is RT? What does that stand for? T is temperature. What's R? Gas. Gas what? Universal gas constant, right? It works all throughout the universe, we think. And then if we use KD, we just drop the minus sign, okay? Because this number is going to be less than 1, and natural log of a number that's less than 1 is going to be a negative number, right? Okay. Okay, so change in free energy. Is the reaction going to be thermodynamically favorable? And that's going to be equal to the change in enthalpy minus the temperature times the change in entropy. And so, contribution of heat to the reaction, we're going to see. So obviously there's going to be a lot of polymerization reactions. There's going to be a lot of covalent bond making and breaking in biology. But when we're looking at these facile associations between proteins and ligands, between proteins and DNA, we don't want, why wouldn't we want to form a bunch of covalent bonds when two proteins come together? Why don't we want to do that? What would be the disadvantage of forming a bunch of covalent bonds? What do you think? Super stable, too stable, the opposite of unstable, right? And so biology is a process, right? We don't want two things to stick together and to never come apart. We want them to stick together to do their job, whatever time frame that is, okay? Microseconds to milliseconds are the time scale that a lot of things are happening on in biology. And then we want them to come apart, okay? And so that's why when we're looking at these association reactions, we're gonna take advantage of non-covalent interactions, okay? That's gonna include things like hydrogen bonding, salt bridges or ionic interactions, okay? And van der Waals interactions, right? And I'll talk more about that when I start talking about protein structure. Okay, so change in entropy, that's a little trickier to get a handle on, okay? And so the two big ones that we're going to be thinking about are basically involve changing what's referred to as degrees of freedom, okay? And for right now, you're gonna think about degrees of freedom in terms of vibrational motion, translational motion, and rotational motion. For the problem I'm gonna have you work today, you're gonna ignore vibrational motion. But if you think about just a spherical particle, okay, so let's pretend this is a protein. It can go side to side. It can go up and down, and it can come in and out, right? So it has 3 degrees of translational motion. and this may not seem right, but it's just the way that the math works out. It also has 3 degrees of rotational motion. And this is in a classic Cartesian coordinate system, right? Because it can rotate this way, it can rotate this way, it can rotate the other way, okay? So it can rotate along all 3 of its axes. Okay. And we're also today, and probably for the most of the class, we're going to ignore changes in water entropy, but I will talk about that just a little bit. All right, so I think, yeah, I went through most of this. So delta H is also related to changes in covalent bonding, right? But like I said, for most of the things we're going to be talking about this semester, it's going to be non-covalent interactions that are kind of driving the different processes. I'll talk more about van der Waals bonds. That's a little tricky to understand. And then we're just going to talk about these 6 degrees of, or your problem is only going to necessarily use the 6 degrees of freedom that I was talking about. Okay, so delta G, if we know enthalpy and entropy, we can get delta G. But if we know the association or dissociation constant, we can also figure out what delta G is, right? We can calculate it directly from the equilibrium constant. And so in this case, this would be association. If you have dissociation, then you're going to lose the negative sign. Okay, so here's the strength of the different types of interactions that we're going to be dealing with. So the first one is covalent bonds, and you can see that covalent bonds, they don't change their energies, whether they're in a gas or they're in water, right? And that makes sense. You've got formal sharing of electrons. It's not really going to matter whether or not there's water around, okay? But all of these other guys, all of these weak non-covalent interactions, you can see that ionic interactions are quite strong in the gas phase, but if you put them in water, they get really pretty weak, right? Hydrogen bonds, stronger in the gas phase than the liquid phase, and then the van der Waals interactions, they don't really change very much. And so we got to consider intermolecular interactions with the water. I'll talk more about that later. But I think for the last problem today, all you need to do, I want to show you this. This is like kind of a nice model. And I'll show you some other models that show better kind of ligand binding, okay? And we'll have a couple of days of an exercise where you guys will actually get to model protein structures on your computers, okay? And so you want to come talk to me if you don't have a laptop type computer, because you might need to rent one or borrow one from the library for the exercise that it's going to be over this short period of time. We got about a month until that happens, okay? But this is just showing some of the different types of interactions that we can have. Here's ionic interactions, right? Remember, they're going to be between formal negative and positive charges, okay? So negative and positive are going to attract. Van der Waals interactions, those are a little trickier. Does anyone sort of have an idea of how van der Waals interactions work?
It's like two things should just naturally attract to each other by existing. It doesn't have to have like special.
Yeah, so that happens with the ionic, right? And it happens with things that have permanent dipoles, but your CH3 groups, they're fairly neutral, right? And so how are we going to get an electrostatic attraction between something that doesn't have a dipole?
Electrostatic dynamics influenced by electrons moving in one direction, influencing nearby electrons of other atoms.
That's right, that's right. So you guys understand the notion that electrons have this probability of being different places in space, right? And every now and then they're going to bunch up on one side of the molecule, and that's actually going to induce the opposite effect in the adjacent molecule, okay? And we're going to see that the tight packing that we have in the center of proteins causes this to happen, and it really amplifies this effect. So it's called an induced dipole effect. You only have it, based on this fairly low probability, but once it happens, those little dipoles start reinforcing each other. And you can see from the energetics that it is the weakest type of interaction that we're going to be dealing with, but we're going to add a whole bunch of these together inside the center of the protein, and that's going to help hold things in place. Okay, so let's think a little bit more about entropy. And so definition of entropy is on the top there. And I've got it in terms of products and reactants. And so WP is going to be the degrees of freedom for the product, and WR is going to be degrees of freedom for the reactant. And so I told you that individual particles have 6 degrees of freedom, right? And so what's my total number of degrees of freedom here? And these slides are posted, guys, right? So what's my total number of degrees of freedom on the left? If you got three rotational degrees of freedom and 3 translational degrees of freedom for each particle, what's it going to be?
6.
12. Okay, what about on the right? 6. We've taken 2 things and we've turned them into 1, okay? Okay, so we've reduced the entropy. Is that energetically favorable? Does entropy spontaneously increase or decrease?
Increase.
As the universe ages? We're headed for entropic death in, like 10 billion years, right? So entropy normally increases in spontaneous systems, okay? And so think about that. You're going to need to use that information for the last problem on the problem set. By the way, where did my sign-up sheet end up? Who's got the sign-up sheet, and who hasn't signed the sign-up sheet? So make sure you sign the sign-up sheet. This is for first day attendance, right? Okay, you can go ahead and start on the last problem.
Can you go back to entropy estimate real
Yeah.
quick? Thank
Yep.
you.
And so WP is your degrees of freedom for the product, and WR is the degrees of freedom for the reactant. Okay?
Thank you.
Yep. Back again?
No. Can you just re-explain the degrees of freedom idea once again?
Yeah, so I can walk this way.
Yeah.
I can walk this way. And I can maybe go up a little bit, right? Kind of big for that. And I can turn this way. I could roll forward, or I could roll sideways. Okay. And so in a classic Cartesian coordinate system, you know, it's much easier if we switch to polar coordinates, but we're not gonna do that.
Yeah, yeah.
It's just gonna be a simple exercise, right?
Uh-huh.
So each particle, not counting vibrational modes, right?
Yeah.
And vibrational modes is a big deal, but we're gonna skip that,
Spin.
okay? And so each particle has 6 degrees of freedom,
Uh-huh.
okay? But remember, in this example, we're taking 2 particles that each have 6 degrees of freedom, and we're converting them to one particle that only has 6 degrees of freedom now, right?
Okay, yeah.
And so when they're apart, there's 12. When they're together, there's 6.
Got it.
Okay?
Thank you. That makes more sense now.
Yeah. Okay, who hasn't signed? I got one more. Everyone signed? Right? Okay. Okay, work the last problem and then you're free to go. I need my beads and my plates back. And you guys can talk among yourselves. You can work in your groups today, okay? For this problem.
H.
What do you use for
Delta H? Don't know. Let's look up what the energy
Did you
approach.
get 1.37 for delta S?
But the
0.69.
0.69.
What is the edge?
Is it negative? I think maybe it's negative 6.
The delta S are times like
The natural log.
Wait, did I-
Yeah.
Did I set this? Did I set these two numbers up correctly? Which one is the product and which one's your delta?
Yeah, it's just 2. Ln 2.
Yeah, negative.
We're just gonna assume negative 20.
Yeah, isn't that just 1?
Then 120 kilojoules per mole. And then
It's not
we minus 310.15 multiplied by 0.69.
So the natural, so H is negative 1. Plus H is negative 1. And then the delta S, what?
it's always just one.
Hey guys, sorry about that. I ran over, all right? And so if you haven't finished the last one, don't worry about it. Everyone will get credit for it. I'll post the key by like Wednesday or something like that, okay? Yeah.
For your delta S, R times Ln, WP, and WR, is it measured in joules per mole or kilojoules per mole?
I gave you the gas constant in calories per mole. And I gave you, on that one slide, you've got the hydrogen bonds in calories per mole. You can do it in either one, though. You can do it in either one. Right?
Yeah, I got you. Thank you. Calories you have to multiply by 4.1. I don't remember what the.
We have on the slide before, but now
You did that H though. What do I tell you? 6 hydrogen bonds.
I wish I could figure out how to do it.
And the hydrogen bonds are on that one slide. They're 1 kilocalories.
4.2.
So that'll give us the value of delta H.
Yeah. Sorry guys, I'll do better with the timing next time. Okay? But let's go ahead and hand things in. Yeah, you can keep the handout on the activity, but I need your problem set. Make sure you put your name, your U number, and your section number. It's all same section, section 5.
Something like that. Fine. What do we do with it?
Keep it.
Alright.
you giving this to me? Or are you just placing it?
Oh, sorry, I meant to just put a different